Here. Okay, great. We have Sid Banerjee from Cornell. Continue on transportation.
Thank you. You good? Okay. Great. So thank you very much for the invitation. And yeah, I guess Dick was mentioning this is somewhat a continuation of the previous talk in multiple senses. So I'm also at Cornell, but this was work which I did when I was at Stanford as a postdoc, and so it's joint work with Ramesh Johari at Stanford, and also Carlos Riquelme, who's a graduate student in the ICME group at Stanford. But perhaps at least definitely want to draw your attention to the last line. So the big credit for the work goes to the data science team at Lyft. And the way it came about was we had been playing around with some of these problems, and we just happened to be at the right place at the right time. And this was 2014, and Lyft just started trying to think about doing dynamic pricing, and we thought we could solve it in our usual hubris. And so Lyft said, sure, come over, solve it. And then So I sort of spent a summer working at Lyft, actually writing out the dynamic pricing stuff. And I think the one thing I learned is like real systems are just nothing close to what we think they are in the models. Or there were all sorts of strange things going on when we were initially playing around with it. And at some point of time, we sort of figured out something which started working really, really well. And we did a lot of A/B tests, compared it to just static pricing, and it still seemed to do very well. So then what this work is it's going to be different from most of the other talks in that there is no data. There is a big reason that there's no data. In particular, there is a certain big brother sitting around in the room or not in the room, but around and so exchanging data for any of these companies is pretty tricky. But really the point of this talk is at least how we think about dynamic pricing and ride-sharing platforms and why we think it seems to work very well, but sort of on a broader level, what are the interesting problems that are coming about in this sort of next wave of online marketplaces, and why I think we have the right tools for solving some of these. So before I even jump into ride sharing, this is a quote. So I think Microsoft published this, had this website earlier in this year where they asked all the top people in Microsoft, what do you think are going to be like the top developments in 2016? This is Preston McAfee, who I think is the chief economist at Microsoft. He is not surprisingly talking about economics. The thing which I like, and I'm definitely biased in this regard, is what he says right at the end about Uber. And the fact that in some sense, a lot of people, in all the excitement about all the data that is being released in all these marketplaces, they tend to overlook the fact that one really, really unique aspect of these new companies is that they're marketplaces. So there is a sort of wave of companies coming in and trying to enter into various aspects of just economic life or like day-to-day interaction. But instead of doing it in a conventional way, they are doing it in this way of setting up a marketplace, essentially defining the rules of the game and then sort of letting it play out. And Uber, Lyft, Airbnb are perhaps like the standard bearers of this, but there are many other interesting problems in this regard. And in some sense, what I'm really interested in and what I'd like to encourage a lot of people to start thinking about is what I think is the role of real-time decision-making in these new online marketplaces. And in particular, if you talk to an economist about this, or if you talk to a lot of people, there's a sense in which there's nothing new which is going on. We have seen all of this before. Economics has solved all these problems. They're slightly different. But it does feel to me that by saying that, we're sort of somewhat missing a crucial point, that there are certain specific features of these marketplaces which I don't think have been seen before. And at least to me, it's not obvious that all of this collapses to everything that we know about online marketplaces. Now, Amin gave this excellent talk about ad auctions today. And in some sense, we could have before, like in the early days of ad auctions, said that we know everything about auctions, let's just run it. But there is a sense in which the theory community has made a very, very fundamental contribution in how ad auctions are thought about. And I do feel that in many of these new marketplaces, perhaps not all, but in many of them, there will be sort of new challenges which come about, especially because we have these sort of new technologies for monitoring and controlling these systems. And now, I don't think we will have maybe an overarching theory. There are a lot of interesting sort of theories about dynamic mechanism design, which Amin was mentioning, but I do think many of these marketplaces have sort of interesting eccentricities which you need to sort of target differently, and you can get very rich problems from these settings. And so that's kind of the high-level context within which I want to place this work we did on rideshare platforms. In particular, the thing which got us very interested in rideshare platforms, well, firstly, I come from a queuing background, and this seemed like this should be a queuing network. But there is a really, really odd thing about these platforms, which is quite different from many others, which is that it is one of these rare markets where the platform sets the transaction price. Now, we could argue why this is the case. We have all this amazing theory about optimal mechanism design. Why do we not just run a second price auction between drivers and passengers? One weak argument here is that that was tried. There was a company called Sidecar which tried doing that, where people could put up prices and people could choose who they wanted to go with. Notice the operative word was in the previous sentence. It seems like it doesn't work. And the reason people think it doesn't work is, in some sense, what Uber and Lyft are providing you is just transportation. It's a taxi service. I don't want to solve an optimization problem when I ask for a taxi. When I ask for a rental car, sure, I spend some time doing it. I sort of go through all my options. When I do airline tickets, yes. When I get out of a restaurant and I want a taxi, I want it fast. I want a sort of low friction environment. And all the companies in this space have very quickly sort of gravitated to this point where there's almost no friction. You press a button, a car comes by, you're happy with it. And of course, in doing that, you've sort of taken away a lot of the control of, or a lot of the power of the marketplace to do optimization. And in some sense, the platform has taken it onto themselves. And that's the thing that we are interested in. Now, I'm hoping most of you all have used Lyft or Uber. But in case you haven't, this is roughly how it works. So the way these ride-sharing marketplaces work, it's a set of paired apps. This is the view that a passenger gets. So as a passenger, you sort of sign on to these platforms. In the case of Lyft, yes, sorry.
Just curious, is there a reason you call it a rideshare instead of a taxi platform?
Yes, and I'll come to that. OK. We could argue about that, but there is something fundamental. So, OK, I think I'm using that to make a distinction that this is a marketplace. This is not someone who is employed. The driver is not employed by the company. A driver is really an independent agent who can choose when to work, where to work, if to work. So Uber and Lyft are not taxi companies in the sense that they do not, except in New York City, employ people. They just set the rules of the game and let it play out. And that's what we want to look at. Fair question. But OK, so the way it works for a passenger is that you open the app, you see a bunch of vehicles around you. You're basically given an estimate of when the nearest vehicle is, and there's various modes you can choose. You request a ride, you get matched up with a rider, you take the ride. At the end of the ride, you are quoted, or you're told the price of the ride. Now, there's a standard formula which is available on the website for each city. It's basically just some constant plus a linear function of distance and time. You pay this and you go on your way. It's completely frictionless. If you don't want to, you really don't have to deal much with the driver. You can give destination online. So a lot of the benefit of these platforms is in that they're completely reducing the friction of taking a taxi ride. You don't have to stand at a street corner and compete with people. You don't have to decide how much tips to give, et cetera, or you don't have to feel guilt in giving or not giving tips. All of that friction has been removed. So that's a huge advantage. But the thing which, in some sense, seems to get much more press and sort of why people think these platforms are doing really well is the fact that because the platforms have taken the ability to charge prices onto themselves, they can actually now charge dynamic prices. So how does dynamic pricing work? As I was saying, the formula for the price of a ride is some linear function of the distance and the time plus some extra fees. In addition, at the beginning of the ride, in this screen, you will also be told if you are in prime time or not, or if there is surge pricing or not. And so the app will tell you a priori that if you want to ride right now, you're going to pay 25% more than the regular fare, or 1.25 times the regular fare. And this is how it looks like when at the end of the ride, this person took a ride on January 31st at 12:35, clearly a time when there is much more demand than supply. And so they actually got quite lucky in that there was only 25% prime time. This is a pretty old picture. And so this was the extra amount that they paid. So, I mean, if you start reading about any of these ride-sharing platforms, at least in the popular media, there is a sense in which this is the thing which will completely rule the world. The fact that they can do dynamic pricing clearly gives them this huge advantage. And sort of embedded in that narrative is the story that it's obvious dynamic pricing can give you a huge advantage. I mean, duh, it's like economics 101. And I don't think it's that obvious. Now, there's a subtlety in the way dynamic pricing is done, which is that now it is clearly obvious that the demand is not the same at different times of the day. So you should be, during the morning rush hour, there's much more demand than supply. In the afternoon, there's much less demand than supply. However, a lot of this is actually quite predictable. So you know that during the morning rush hour, you may not know exactly, but you do know that there's much more demand than in the afternoon. And the idea of actually charging different prices in the morning rush hour or in the afternoon or at night, that's actually not new. So, I mean, I remember as far back as when I was growing up in India, when you took a taxi ride at night, you used to pay, 50% extra or something like that. And this was mandated. This was part of the sort of fee structure agreed on by the government that you're going to pay more at times of greater demand. So the point of dynamic pricing, and I think this is what a lot of people think about it, is that it's not that you can charge different prices at different times of the day. That's clearly a win-win, but that can be done even by taxis. You could always have a sort of a schedule of rates that you charge at different times of the day. Now, the thing that people don't realize, or I think by now a lot of people do realize, that Lyft and Uber actually change prices on a much faster time scale. So it's on the order of minutes, maybe even faster now, and on something like a 3-block by 3-block radius, or maybe even smaller. So you're really doing dynamic pricing on a very, very fine-grained sort of geographical and time basis. And at that point, it's not obvious to me why exactly is this doing better. So you, in some sense, you are not reacting to these sort of large-scale changes in the average demand. You are reacting to stochastic fluctuations. And you're doing it in a system which is sort of very complex, where rides are taken up, they end somewhere, it's the number of drivers keeps changing, et cetera, et cetera. It's not immediately obvious that dynamic pricing is buying you anything. And so that was the problem we went in to try and look at. So this is a graph of, or this is a map of San Francisco. It's from this website called What's the Fare, which actually like collects quote or primetime quotes from these companies, or you can query both the companies to see what the prices are, and it sort of collects this data, or at least used to. And you can see that, okay, during the morning rush hour, most of the demand is in the outskirts. There's less demand downtown. It sort of reverses in the evening. So this is actually showing the prime time, but in some sense, the prime time is reacting to, or the average prices are reacting to the average demand, which is actually quite predictable. I don't have data to back this up, but the companies do have pretty decent demand predictions about the demand. There's also a sort of hidden thing about these systems that, unlike bike sharing, there's actually no censored demand in Lyft and Uber. So the friction in opening your app and looking for a ride is really, really small. So you're actually seeing everyone who is, you're seeing most people who are looking for a ride, you're seeing exactly what's the time and price they were quoted. You can form very good models of whether they wanted a ride or not. This is all very predictable, but the question is, why should we then sort of do this dynamic? And I'm using the word quasi-static to sort of distinguish that really what I want to compare this fine time scale dynamic pricing is with something which reacts to the average changes or the average demand and the average elasticities in a time period. So not a price which remains constant throughout the day, but something which, like, we could just, for the purpose of this talk and for this work, what I'm imagining is that the demand remains constant for some time, then it changes its block Markov, and we can change the price to react to that, or we can change the price to react to stochastic fluctuations. What I'm trying to ask is, what is the latter buying you over the former? And immediately once you formulate the question, you realize that in order to try and address this question, it's not sufficient to just think about the strategic behavior of passengers and drivers. You also really need a model which captures the dynamics of the platform. So you cannot talk about fine timescale dynamic pricing without actually having some sort of dynamic model for the platform. And that for me is excellent because my background's in queuing theory, and clearly this should be a queuing model, and that's where we're going to go to. But you also, in addition to the dynamics, you do need to, the control that you're doing is through market mechanisms. You're controlling things through price, and so you really need to think about the strategic behavior of both the passengers and the drivers. And this is coming back to your question that the drivers are not employed by the platform. They have the agency to join or not join the platform. And you also want to think about, why is the platform choosing these policies? What are their objectives, and what can they do? And what I'll sort of try to convince you is that you can come up with models which seem sort of to model a lot of these phenomena, but they're still somewhat tractable. And kind of surprisingly, what at least we get when we think about this problem is that there's a sense in which doing this sort of dynamic pricing over the stochastic fluctuation is not fundamentally better than static pricing. So if I was sort of completely omniscient and I could choose exactly the right price, there is an exact right price which I could have chosen for each time of the day. But there's a sense in which it is buying you a lot of robustness, or it is sort of learning certain parameters and kind of smoothing over the fact that maybe you can't predict everything exactly, or maybe there are sort of unexpected events which you can't take care of. So the reason why, at least we think at the end of this exercise, and this is a completely theoretical exercise, but we know dynamic pricing in practice works really well. We posit that the reason for that is not that it is fundamentally better, but it is sort of much more robust compared to doing anything static. That's what I'll try to talk about. And kind of in terms of where this work fits in, there's actually a very nice literature which started roughly around 2003 by Roche and Tirole, and followed up by a bunch of other people on thinking about two-sided marketplaces. And the idea that in many of these two-sided marketplaces, if I enter a marketplace like Lyft or Airbnb, in addition to the price that I'm charged by the marketplace, it's also very important to know who else enters on the other side of the marketplace. So the simplest story is, if you're in a dating market, sure, they charge you a subscription, you decide whether to pay that or not, but you also decide whether to enter based on how many people enter on the other side, who are deciding whether to enter based on how many people enter on this side, and vice versa. So in order to actually say something about these markets, you really want to think about the equilibrium that emerges from this game. And Roche and Tirole and Weil and a bunch of other people sort of came up with a bunch of very stylized economic models about how you should think about these marketplaces. And on the other hand, there is a sort of older stream of literature on revenue management, and a very rich literature on revenue management. In particular, there's this seminal work by Gallego and Van Ryzen all the way back in '94, where they were thinking of something like airline pricing. You have a bunch of seats, and you want to sort of price them against a stochastic demand. And they basically came up with a sort of optimal way of doing dynamic pricing if you exactly knew the demand. And there's a long line of work following on from that. But the crucial assumption in all those works is that your resources are given to you at the beginning. You're sort of given an endowment of airline seats, and you're trying to decide what best to do. And so one of the surprising things that comes about is that Gallego and Van Ryzen actually made a very similar observation that in sort of an appropriate limit, there is a sort of single static price, but dynamic pricing, again, in that setting, seems to buy this sense of robustness. And it's for completely different reasons. And one of the things which we are still trying to figure out is like, what really are the connections between, why are we getting something similar? And I'm kind of putting a bunch of other work. So there is a lot of sort of progress more recently in queuing networks, where we can model richer queuing networks. What I have done, or what we have used, is actually a much older model of what are called Jackson networks, but there are many other settings which are better modeled by many of these newer sort of stochastic models which we have. And I think there are a lot of interesting questions about how we can fit these to sort of real marketplaces and how we can control them. Okay, so that's the background. Okay, what exactly are we doing in our work? Well, so we're going to just focus on a single block of time. So think of this as the morning rush hour and a single region. So morning rush hour, downtown San Francisco. And the main idea over here is that we're going to assume that all the mean system parameters stay constant. So there is some sort of average demand, there's an average supply of drivers, there's sort of these price elasticity functions, cost elasticity functions. All of this remains constant in this block of time. This is, of course, a very sort of simplified assumption, but we'll sort of go with this and see what we can say in this case. And in particular, what we're going to do under this assumption is we're going to build a stochastic model to track the number of free drivers in the system. So how many drivers are waiting around in this region for someone to come and give a ride, to take a ride. And for simplicity, okay. Now what I mean by dynamic pricing here is, since I'm keeping track of the number of available drivers, this is an instantaneous state variable, which is continuously changing over time. And I'm going to set a price for a ride at any time, or this multiplier for the ride, as a function of the available drivers at that instant in the network. I'm also going to assume that the platform earns a fixed fraction of every dollar spent. So this is how it's done right now. It's unclear if this is optimal, but just to keep things simple, that's what we're going to assume. So that's the high-level story of the model. To kind of the main thing which is going to drive all of our results, and this is something which I think is fairly fundamental in this setting, but is also true in many other settings, is that there's a sort of fundamental difference in the time scale on which the two sides react to the marketplace. So if I'm a passenger and I've just got out of a restaurant, I'm not sort of reasoning over the long time to decide whether I want a taxi ride or not. Like, how much money do I have? Should I save it up? Should I invest it in stocks? No, I just look at the price and go, do I want the taxi or not? On the other hand, and this is something which we can test looking at data, the drivers are definitely sensitive to their long-term earnings. So they don't care about whether this instantaneous ride is under surge pricing or not. I mean, initially some drivers care, but they very soon realize that there's no point trying to predict that. What they really care about is, at the end of the day or at the end of the week, are we making enough money to make this worthwhile? Or maybe we have an outside option. Sorry, yeah.
So there's this argument that surge pricing or dynamic pricing will lead to more
drivers on the road. Yeah, I don't believe it's true. So the typical time, I mean, just sort of as a thought experiment, the time it would take you to react to surge pricing and go somewhere would be on the order of 10 or 15 minutes. The prices are changing every minute. Now, that's not proof. One of the things which I can say, so both Lyft and Uber have done a lot of experimentation with what they call heat maps. So they show the drivers what the surge looks like. And as far as I know, both are sort of unconvinced if this is doing something which they know. And definitely, if you just show prices, there is a sense in which drivers miscoordinate. So initially, they start driving towards the heat, and then they go, oops, it's gone. They sort of go somewhere else. If you talk to most drivers, after a point, they just sort of stop looking at it. They know in their head that certain areas are good, certain areas are bad at certain times of the day, and they just follow that. So they're not reacting to things instantaneously. So it's not that that is untrue, but I'm going to try and claim that it's true in a more subtle sense. It's true in an equilibrium sense, but not on an instantaneous sense. Okay, that makes sense. So another thing you may sort of take issue with, or someone may take issue with, is I'm saying that drivers are sensitive to long-term average earnings. You could ask, well, how exactly are they learning this long-term average earnings? This is actually made very simple by Lyft and Uber. They actually send out a mail every week to all the drivers, which basically says, this is how much money you made. Now, Uber is saying you could have earned $217 more, but really what the information they're giving is, these are the times of the week, and this is how much money drivers made at different times of the week. So as a driver, you have complete freedom to choose when you want to work, where you want to work, and in particular, if you want to work at all. Is it worthwhile at all to work on the system or not? So instead of really sort of thinking about learning dynamics, they're sort of just shortcutting it. They're giving you the information and saying, do you want to work or not?
Sorry, I've never seen the driver's side of it before, so I find it fascinating. What's the basis for that $217?
I don't know. I don't know, and I'd be a little scared if there is an exact answer or not. But I mean, you could sort of calculate on the basis of this would be my conjecture. They're looking at how many hours you drove, and then they're sort of saying if you had shifted it a bit and driven in other hours, assuming everything else is a constant, I know how much drivers made on average in those other hours. So even just assuming, this is at least the sort of first cut I would do that. Assuming you drive the same number of hours but shifted it a bit, how much more would you make? I think you can sort of dig deeper into those, and they do give you more information, but I've also actually never seen the driver's side, so I'm not sure.
Also, my eyesight isn't good enough, so I can't read the text.
Yeah, so this I can't either. So this is not from Lyft. Lyft is, again, they don't really publish this. This is from a third party, but it's very similar. It's sort of saying there are hours, and they're sort of saying what was the average value drivers made in those hours.
That's the average of all other drivers.
All other drivers in the same region. So there's another sort of website where you can go where they'll break it down by region. So should you drive an SF? Should you drive? And there is definitely driver heterogeneity. So I've talked with drivers who had like back problems, and so they don't want to drive during the rush hour because they don't want to be stationary for too long, or people who just don't like the rush hour and things like that, or have kids and want to go back home.
Time scale on that is hours?
Hours, yeah. I'm sure they A/B tested that and found out this is best. So I'm not going to defend this exactly. I'm just sort of using this to say that there's a sense in which a lot of the learning is short-circuited. Information is given back to the drivers, and drivers can act upon that. So how should we fit this into the model? So this is how I think of the ride-sharing system. So I'm imagining a queue of, or just a birth-death chain of the number of available drivers in a region. And I'm imagining that that number is increasing at some rate lambda. Now, where does this lambda come from? Hold on a second. So it's increasing at some rate, it's a Poisson rate lambda. On the other hand, there is a rate mu naught of passengers arriving to the system looking for a ride. So this is just people opening their app looking for a ride. Now, when they do that, they are sort of shown two things. Firstly, they're shown how far the driver is. In my case, I'm just assuming they're shown, is there a driver there or not? So I'm sort of making that binary, but they're also shown a price. And my assumption is that each passenger has some distribution over the value for the ride. So they're drawing their value IID, then they look at the price and go, yeah, okay, sure, my value is higher, I'm in the tail, so I'll take it or I won't. So you take this mu naught, which is the actual rate of arrivals, and then you're sort of winnowing it down using these prices. And the pricing policy I'm going to think of is a really simple one where I have a threshold on the number of drivers. If there are more drivers than that, I'm going to charge a lower price, so this queue actually drains much faster. As soon as I sort of hit this threshold, I charge a higher price, it slows down the queue. So this is sort of the passenger side. And passengers, I mean, if they see a price they don't like, or if they say no drivers, they just leave the system. So it's a blocking system as far as they are concerned. Is that clear? Just from the passenger side? Okay. So what's going on with the drivers? Well, we can take the same model and kind of embed it in a larger queuing network. So what I'm doing here is these were the available drivers every time they got matched up. So this is what's called a MMN1 queue, if you're interested. Whenever they get matched up, they basically give a ride. So if there's some busy time, we can model it however we feel like. This doesn't actually matter that much. This is a crucial assumption which we make, which is that at the end of the ride, the drivers independently, with some probability queue exit, just decide to get out of the system, so turn off their apps, else they come back. Now, there is evidence that this does not happen independently. It happens based on whether you saw prime time, blah, blah, blah. But in some sense, this is a really, really noisy process because, again, many of these drivers are both on Lyft and Uber, so they may just switch apps, or maybe they just wanted a coffee. So in some sense, you definitely see drivers going in and out. And to simplify things, I'm modeling them as sort of exiting independently and sort of entering at a certain rate. Every queuing theorist in the room is going, no, that's not why you're doing it. You're doing that because it's a Jackson network, which is also true. I am sort of deliberately setting it up in such a way such that this model is easy to analyze. And the reason I'm doing that is now, once I set it up, I can go back and ask the question, well, why are the drivers entering into the system? And one sort of typical way of thinking about it is that the driver has some minimum rate of earnings that they want to have. So they have a reservation earning rate. We could think of this as this is the other work they could have done. Maybe they could have worked somewhere else in that time. They would have earned something. They need a certain minimum amount before they're even interested in entering the platform. So each driver, there's sort of mass lambda naught of drivers who can join the platform. Each one of them is making an endogenous entry decision. They know what the average value they're going to make, Based on that, they're deciding should we come in or not. And the way I'm calculating that is as follows. So each driver has an individual earning rate. Now what they're going to calculate is for each per ride, what's the expected per ride earning. This is not constant because, again, the per ride earning depends on when you got the ride. But it's the expected per ride earning divided by the expected time they spent in getting that entire ride, which is the ride time, but also the time they waited for the ride. Because they're not being employed by the company, they're actually, this is a loss for them. If you're waiting for a long time to get a ride, you're not making any money in that time. And then sort of appropriately normalize. So the lambda over here, the lambda in our previous picture, is really coming about as a result of an equilibrium computation, which depends on the average performance of this queuing network. To make this, okay. So that's sort of the complete model. So this is the passenger side. This is sort of embedded in a queue. And then the drivers are making endogenous entry decisions based on what's the average performance of the system, which is affected by the driver entry decision. So if you're, why I mentioned the sort of Rocher-Tirole et al. Papers before, there's a sense in which they really try to capture the same thing, but they sort of capture it using these exogenous functions. They just say, this is the utility function. Whereas what we are doing is we are saying, well, no, in order to talk about dynamic pricing, I really need to understand the dynamics to determine what the utility function is and what the correct equilibrium to look at. And what we want to study, just to keep things simple, is we want to look at the throughput of the system and see what we can say about it. So again, sort of to summarize, this is the problem which I want to look at. I want to sort of think about how I design pricing policies so as to control this equilibrium where the passenger arrival rate depends on the price they see when they enter. The driver arrival rate depends on the average value they get per ride, and sort of put this entire thing together and see what I can say about it. So okay, I pause here because that was a lot. So any questions about questions, comments, criticisms? Okay, minor criticisms, things which can't be taken offline. We're good? Okay. Okay, so what can we say about this? So we want to look at the pricing policy and how it affects the equilibrium. Oh, okay, good, yes.
A couple quick questions.
Yes.
Does this system allow you to put alerts in to tell you when the price meets a certain point for the driver or the passenger, or is it?
Can you say that again? I didn't get that.
Does the system allow you, and I don't know if this is a setup system or it's a design, but does it allow you to put in alerts to the driver or the passenger?
Yes.
To say that something hits a certain price point?
Yes.
Like
So
high or low price point?
Uber does now do it for passengers. They do sort of tell you something like it's prime time right now, but we can send you an alert if the prime time price is reduced. I have never successfully seen it reduced, but then I don't use Uber too much for certain reasons. Does that affect? I mean, it just sort of makes things more complicated. So we can extend this a little bit and say something like, well, I can give you an average wait time till you get a ride or an average time till you get the correct price you want. I'm pretty sure so what I'm going to do very soon, again, because I do queuing theory, I'm going to scale the system in a certain way. The thing that you're mentioning is going to get washed out in the scaling. So the sort of effects I'm looking for are kind of much larger scale effects than what you're asking for. So that can be modeled. It's going to wash out in this scaling, but it definitely has an impact. So in no way am I telling you this is the optimal design, which is exactly what is used. This is kind of a thought experiment to understand why is dynamic pricing working.
I was saying that if you had those mechanisms, it would actually attract more drivers and more passengers.
They definitely try that. So it's quite likely, but I don't think it will change the first order effect of the platform. But I will say I haven't. The question about giving alerts to passengers, I have thought a bit about, and that won't affect. For drivers, I haven't thought about it, but I think it won't affect. But that, to be completely fair, it's not in this model. So, sure. Anything else? Okay. So as I said, okay, we can show that equilibrium exists under some conditions. It's unique, so we can do the sort of due diligence on this. It's not. I don't have a formula for what the equilibrium is of the system, but I can at least, I can compute it numerically. And so what I'll try to show you is what we can say numerically and a particular limit under which we can actually understand the system, which is I'm going to scale both lambda and mu up to infinity, and then sort of rescale the number of rides. So one way of thinking about it is I look at this video of this lift system, I run it, play it faster and faster, and then sort of rescale it back. And in that limit, I can actually say something and optimize the system. So that's what I'll try to show you, and I'll try to show that to you in pictures. So what I'm showing here is the static pricing. And what's going on here is I'm actually using a single price and trying to find the equilibrium number of drivers or the equilibrium rate of rides in the system. If the price is too low, drivers don't want to work. If the price is too high, passengers are now upset, and actually the driver idle time is going up. And so you get this sort of complicated looking diagram as you just vary the price. And you can basically now scale this system by scaling in and renormalize it, and you sort of get these sort of sequence of curves. And remarkably, in the limit, you can actually exactly characterize what this equilibrium looks like. And what it looks like is it looks like the minimum of two functions, one of which is determined by supply, one of which is determined by demand. If you were an economist at this point, you should turn your head this way and look at it from this way. This is exactly a demand-supply curve. I didn't set out to try and get a demand-supply curve. This was just sort of coming out from the natural micro foundation. So once we got this, we were like, OK, in some sense, maybe we are doing something right. This seems to make sense. This is what we would expect. What can we say about dynamic pricing in this setting? So I can play the same game again. So in the case of dynamic pricing, now it's two variables, the two prices. So I'm doing this two prices, single threshold. What I'm showing in this plot is I'm sort of choosing one of the prices fixed over here at 1.75, and I'm varying the second price over this range, sort of in the background choosing an appropriate threshold, and then I'm finding the equilibrium. So you get some weird funky shape, different from the static pricing. It exactly meets the static pricing when the two prices are equal, so it seems reasonable. Now I can play the same game of scaling up the system. Observe what's happening as I'm scaling it up. It seems like the sort of maximum is getting closer, and you can keep playing this game, and sort of lo and behold, at the limit, the maximum values actually collapse. So the throughput, the best throughput that you get under dynamic pricing, and at least with this one single price, seems to collapse exactly to the best throughput that you get under static. Now, we did not, I was actually really disappointed when I saw this. Initially, I thought this was just the simulation. I kept trying it with a bunch of other cases because I expected a phase transition here. But lo and behold, you can sort of go back and show under a very minor condition that this one of these functions has an increasing hazard rate. This is actually fundamentally true. So you have a sort of collapse where the dynamic pricing collapses to a single static price in the limit. So this is nice as a theorist. It's extremely disappointing as someone who designed the system and said dynamic pricing does really well. I mean, here I'm coming back and saying, no, hold on a second, it doesn't do really well. So what's going on? Yeah.
Could you give a little bit intuition on
why this happens, or why?
Yeah.
OK, so I like that you didn't ask why is this not obvious. So, so what is going on? So when I'm scaling the system, both my prices, the expected price is changing because I'm sort of doing all these sort of funky scaling of like fixing the two prices but changing the threshold, but also my delays are changing. Now, we know that whenever the system is stable, the system firstly has to be stable, because if it's not, the delay blows up to infinity and drivers are unhappy. So that's kind of clear. So it's clear that the delay is sort of going to zero at a certain rate, but on the other hand, the price may also be decreasing. So it's not obvious that when I sort of scale both of them jointly, this is collapsing to a single price. But there it turns out now, if you look at this sort of hazard rate condition, the extra value that I get, so whenever I'm sort of using the two prices, really what's happening in the limit is the system just oscillates very fast above the threshold. It just keeps bouncing back and forth between that single threshold. Whenever it goes too high, the delay increases, but the price also increases. Then it gets pulled back, delay decreases, price decreases. But under this condition, these two exactly balance out. And that I have no intuition for. That seems to happen just through the algebra. So this just genuinely was surprising for me. We sort of got it from looking at the simulations and then struggling through it and proved it. That's the best. I think Ramesh will disagree. I think he has some story about it, but in some sense, I don't think I can completely explain that aspect of it. What I can explain is the next part. So what in what sense can dynamic pricing be better? Sorry, I'll take just 5 more minutes. So in order to sort of be convinced of this story, a question that one should ask at this point is, great, there is this amazing static price. Firstly, how do I compute it? And the way I'm suggesting you compute it is you do all these sort of crazy equilibrium computation given all the data. Secondly, what if the static price is 2.7172717, some strange value? I can't sort of go back to people and say, you can take a ride right now as long as you pay 2.71727. That just won't make sense. There is a sense in which you don't have complete control over prices. So there are many senses in which, even though there is this amazing static price, it just cannot be implemented. But so how can we sort of formalize this notion? Well, one question I could ask is, what if I had some noise in my parameter estimation? So what if I thought that the demand was actually 4, whatever, this is unitless, I mean, it's just simulations, but the demand, I expected it to be 4, my prediction engines told me 4, I sort of set my prices at 4 and sort of sat back and said, I'm going to earn a lot of money or get a lot of throughput. In the meantime, what happened is there was a sort of 10% shift in my demand, either up or down. What's going to happen, and this is again in the large market limit, the optimal throughput, basically just this optimal static price just goes off a cliff. So in some sense, you're not being able to react to the fact that you miscalculated the demand because there is just no degree of freedom. On the other hand, what I could do is, suppose you told me that, yeah, I don't know the exact demand, but I know it's 4 plus minus 10%. What I could do is I could use the higher demand to sort of set the higher price, use the lower demand to set the lower price, and just let dynamic pricing run. And when you do that, this is the performance you get. And this is, again, sort of more general, and sort of formally what you can show is that if you do dynamic pricing using even just these 2 points, it always achieves something better than sort of the linear approximation of this optimal manifold. Now, why is this happening? This we actually understand a little better. Again, what's happening here is that dynamic pricing, instead of actually improving your system overall, it's just acting as a control device. It's saying that whenever the queue is sort of trying to go away too far, I'm pushing it back. Whenever it's sort of going too low, I'm pushing it forward. I don't need to exactly know what the correct price was. Just by sort of just mixing with these 2 prices, I can sort of bounce back and forth and get the right thing. And you can do it even further. Even if you don't know exactly what region to choose, and you can choose like a number of dynamic prices and do the same thing, and you'll sort of get back results of this sort. So that's the sense in which I was saying that what we think, at least at the end of this, I mean, this is in John's word, in what John was saying before, this is us developing a mathematical model and assigning a narrative to it. But in some sense, it was really perplexing to us as to why exactly is dynamic pricing doing better. And I'm not claiming this is exactly the reason, although there are some sort of predictions this makes which you can go back and test. I wish we had data to do that, but maybe, hopefully, we soon will. But it does kind of point out that there's this very sort of stark but subtle difference as to what we think it's doing. We don't think, at least, that it is fundamentally better than just doing static pricing, but it is buying you a sort of sense of learning or a sense of robustness in the system. And that's really the reason why, in some sense, I think this is the right community to be answering these questions, that there is something fundamental going on here which is outside sort of the basic economics. There is some sort of aspect of control of algorithms which is very fundamental in thinking about these systems. And there are many other questions you can ask in a similar light. So how does better information displays help? How does showing people heat maps help? How does showing people these weekly things help? How does that change their decisions? What if you have longer term contracts? Both Lyft and Uber sort of experiment with promising drivers you'll earn a certain amount for a small fraction of drivers. Does that change things? What happens because there's competition between Lyft and Uber? That's completely not understood. A lot of the decisions are really made in competition. Kind of one thing which I'm really interested in, and I think Neil was talking about this earlier, was that how does this interact with older systems? So is the rise of Lyft and Uber really going to sort of completely destroy a public transit mode? Because that, in some sense, we maybe agree is not the right thing to do. So what do these equilibria look like when we move forward? And just a host of other questions. I sort of specialized it for ride sharing, but you can kind of ask these same questions for many of these dynamic marketplaces. So that's what I'm sort of interested in that's the real-time decision problems which I think we should be looking at. All right, great. So that's all I have, and if you all have any questions.
Just a question from the modeling standpoint.
Yeah.
So you basically took a limit where you let the arrival rate get large in a certain area of the city in terms of both taxis and customers. Another thing you could do is basically it's a Jackson network. You can probabilistically route the taxis to another block or another part of the network.
Yeah.
And then the kind of limit you might take will be a kind of mean field limit, and you could view this as a mean field gain.
Yeah.
Is that something that you might consider?
Oh, definitely. I was laughing because I think Ramesh is watching this at some point and going, I told you so. But one huge thing which is missing out in this model is we are not modeling ETA. We are not modeling the fact that the taxi may be further away from you or closer to you. So there is no spatial dynamics here at all. That is a very, very fundamental fact or fundamental aspect of these ride-sharing platforms that in fact gets even more exacerbated when you start doing ride pooling, when you can have multiple people in a ride and you're really controlling where these cars are located. And there aren't very good models for this. So I think I was mentioning this to Amin earlier, that even just thinking about what the optimal matching is, there's a sense in which there are heuristics which are being used, but I don't think we have a very good sense of what's the right way to do these. So, I mean, this is a very, very sort of preliminary. We are nowhere close to having an understanding of this system like, say, Amin has for ad auctions or the electrical grid to some extent. Like, it's a very, very nascent system. To an extent, it'll help once we get more data, and there are hopefully movements towards doing that soon. But I think that's a great question. Like, what would be the sort of correct spatial scaling to look at? What should be the size of these stations? And what can you say in that setting? Yeah, I don't have a good answer for that. Yeah, we should work on that. Yeah.
I mean, so much power where there's no utility function for the consumer that's really possible. I mean, if you were trying to do this really serious on the consumer side,
Yes.
the issue of long-term
Yes.
satisfaction, you make them angry once, they'll fight forever.
No, that's a great question.
Yeah, so that's what makes it really interesting and challenging. as a consumer.
I think that's another really interesting one. So in particular, one obvious thing I can say, just in this model, the rate at which I don't see a driver or I see a high price should affect the reuse of that platform moving ahead in time. The high price maybe not so much, but if I don't see a driver, maybe I want to switch to City Bike. It's very likely it definitely happens again outside this model. I can say some weak things about it. And so actually the weakest thing I would say is, well, the cost of opening your app and looking for a lift is just so small. The friction is very low. So it's not a first order effect, but it's definitely an important effect which should be considered outside this model. Yeah.
So in the beginning you mentioned that companies like Sidecars have been trying to have like a more full kind of marketplace where people would post bids and so on, right? I'm curious, in your kind of analysis, is there a way to have to compare like what something like that would have done for the same kind of setup?
I mean, for that, I'd need a model for how the passenger reacts to being shown a menu. So this may not be true, but my gut reaction is we'd need to do more sort of behavioral modeling of the passenger before. It's definitely possible to write long-term contracts with the driver or even with the passenger. So Lyft and Uber have long-term contracts with certain companies saying we will give you so many rides, use us for the commute, and you get a better deal. And they've now started this thing called Commute, where if you're coming in from, say, the South Bay, you can sort of set up a regular long-term contract for doing that. I think so if we had to formulate this as optimal mechanism design, I think longer-term contracts with short-term dynamics would perhaps be better than actual dynamic mechanism design. I mean, I don't know. I guess that's partly what Sean was saying earlier in the morning, and it's definitely moving that way. So we will see much more sort of long-term contracts from Lyft and Uber, that you can freeze your rate for the weekend if you pay so much right now, et cetera, et cetera. That stuff's, it should be coming if it's not.
I'm just wondering,
If I were trying to build a platform for taxis, it's just plain impossible to build a platform with static pricing. The only thing you can code is something which periodically updates its pricing. So therefore, anything you build will have dynamic pricing at some timescale. And then if I can run my static pricing script once a month, I can run it every 5 minutes as well, it seems to me.
So to compute the optimal, so then the two things I would say is that
There is no such thing. What my conclusion would be, there is no such thing as a static pricing scheme in practice. You can only ever build a system with dynamic pricing scheme. And then the question is, how complex do I want my dynamic pricing scheme to be? And so the story here is that a very simple dynamic pricing scheme is pretty much as good as something which tries to be.
So I won't go that far. It's quite possible sort of you could do something real time and get better prices. I do think one big limitation at that point is going to be people don't react between like 1.25 and 1.27. So you will, I think that it's almost fundamental that you have to have big enough jumps. And so you'll never be able to do a perfect thing. So maybe you can get a perfect mix between two, but that's really what this is doing.
Well, actually, just not sure I agree entirely with David, because completely different from Uber and Lyft or Grab Taxi, which just beats these guys out in like all of the Southeast Asia countries.
Right.
It runs on top of a regular taxi service, and it's just an e-hailing app. So it's a ride referral system.
Sure.
The drivers and the passengers are both, just using it for everything. The price is pretty static.
Sure.
So if both the drivers and the passengers simultaneously look at both Uber and Lyft and decide which one is better and then choose that. There are slightly conflicting reasons. Passengers want the low price, drivers want the high price.
Yeah, and that happens, and so that's the competition between platform side.
No, but that would mean that since rights need to be given.
I see. You could always just undercut the other person.
Right. And that means the static pricing is actually how Adam's disagreeing with David on these graphics, right?
But it's not static, because you don't hard code the costs into your source code. Any piece of code you write, the price will be a parameter which can be fed in. So the difference between static pricing and dynamic pricing is how often do you want to run a script which modifies, or how often it's a policy.
I think you guys are agreeing actually. So Damon's just saying it just doesn't make sense. If I was to write it from scratch today, why would I do static? Unless you sort of held a gun to my head and said, do static pricing. The government says so, you just won't.
There are very good human psychology or policy grounds for not modifying the price too frequently.
Sure.
But it's not a code issue, it's a data and policy issue.
So if I take that to an extreme, just maybe last comment, one could argue what you should do is you should have a schedule which is published one day in advance, saying these are the prices, and then let people decide. That is not done, and I'm sort of trying to argue that shouldn't be done. Or at least at the moment, that shouldn't be done.
But I thought there's a fundamental difference between static and dynamic. Dynamic means that it depends on the current state. Static means that you can change frequently, but it's independent of current state. You can say that dynamic just means the time scale is 0.
That's fair, yeah.
What do you mean by static?
So
static doesn't mean it's constant over time.
Okay, that's no such thing though on a systems basis. If you're a programmer, you won't hard code the costs into your source code. So I don't think static means anything as an abstraction of the piece of code.
No, but the key distinction I want to...
This is state-dependent pricing. Yeah, so I should actually call this state-dependent dynamic pricing versus... So Stephen's just pointing out I could have a dynamic schedule over time, and that is still different from... So in terms of the system, do you need to query the number of drivers to determine your state, or can you just have a lookup table of prices? I'm saying you have to query the number of drivers, or it makes sense to query the number of drivers.
Just as a comment on that, isn't this kind of similar model to like ad auctions and things like this, where basically 30 people turn up for an auction for 10 places?
But there are...
I understand it's not auction,
yes, but that driver is going to come back, whereas I may not come back to Google. So in that just naive sense, it's a more complex stochastic.
When I see your example, I think like, okay, this 3x3 block or whatever is an ad auction in some sense. The taxis that are in the area,
sure,
in the same as the ads and the slots, and you basically, on that instance, that you have to give an impression and price it according to click-through. And it's sort of the same thing as the person and the taxi matching up in the pricing based on that.
But I mean,
This is an
Maybe
analogy.
we can,
Yeah.
because Balaji needs to leave and we have to have some discussion.
So
Maybe
10 minutes over time or so.
okay, I thought this was the discussion. No, okay, I'm joking. No,
I
I'm
think it's great. I think that's the whole point of the workshop. But maybe we can take it offline for. Okay, let's thank the speaker again. Also, before we forget, I guess.
Oh yeah.